In the vast, predictable dance of our solar system, something utterly alien slipped through in 2017. No, not aliens in a flying saucer, at least not in the way you might think. This was Oumuamua, the first confirmed interstellar visitor we'd ever seen. A cosmic scout, just passing through, except, it broke the rules. It defied the fundamental laws of physics as we know them, leaving scientists scratching their heads and some, even daring to whisper the word, alien technology. This wasn't just another rock from another star. Oumuamua's behavior was so strange, so perplexing, that it forced us to confront the possibility that our understanding of the universe, or at least the objects within it, might be incomplete. What was this object? What did it do that made it so unique? And are there others like it, lurking just beyond our sight? Before we dive deeper into Oumuamua's bizarre tale, let's set the stage. Our solar system isn't some isolated island. It's part of a bustling cosmic neighborhood. Scientists now believe interstellar objects are far more common than previously imagined, potentially thousands, even tens of thousands, passing through our solar system every single day. This might sound like a cosmic traffic jam, but why are these numbers so high? Our solar system extends far beyond the familiar orbits of the planets. Beyond Neptune lies the Kuiper Belt, and even further, the immense, spherical Oort cloud. This cloud is a reservoir of potentially trillions of comets, gravitationally bound to our Sun, yet so distant they exist on the fringes of our star's influence. Many of the comets we see with their majestic tails likely originated in the Oort cloud, on elliptical orbits that take tens to hundreds of thousands of years to complete. But what sends these icy wanderers hurtling towards the inner solar system, or even out of our system entirely? Often, it's the subtle, gravitational tug of other stars as our solar system orbits the galactic center. Even at distances of a couple of light years, these stellar encounters can perturb a comet's orbit, either sending it crashing towards the Sun or flinging it into the vastness of interstellar space, joining the ranks of countless other galactic wanderers. Just as our Oort cloud constantly loses and gains comets through these stellar interactions, so too do other star systems. This means the galaxy is teeming with these interstellar interlopers. As our solar system journeys through the Milky Way, we constantly cross paths with these celestial hitchhikers. Many approach from the direction of Vega, the very direction our solar system is heading. Most are traveling too fast to be captured by our Sun's gravity, merely having their trajectory subtly bent as they pass by. And Oumuamua? It was one of them. Oumuamua burst into our awareness on October 19, 2017, first spotted by the Pan-STARRS telescope in Hawaii. Initially, it was classified as a comet, but something was off. Unlike typical comets, there was no glowing coma, the fuzzy envelope of gas and dust that forms around a comet as it approaches the Sun. It was reclassified as an asteroid, the first object to ever undergo such a reclassification. But the real shock came when its orbit was established. Oumuamua was moving too fast, on a hyperbolic trajectory, meaning it wasn't gravitationally bound to our Sun at all. It was just passing through, destined to leave our solar system forever. It was then given its now famous Hawaiian name, Oumuamua, meaning scout or first distant messenger, and earned a brand new classification from the International Astronomical Union, 1I/2017 U1, the first interstellar object. As the first of its kind, scientists were desperate to glean any information they could about Oumuamua. And what they found was truly strange. It was small, estimated to be between 100 and 1,000 meters long, and its brightness fluctuated dramatically every 7 hours, suggesting an incredibly elongated, possibly cigar-like, or even pancake-flat, shape. It also appeared to be tumbling chaotically, not rotating along a stable axis. But perhaps the most intriguing puzzle was its nature. If it was an asteroid, meaning it originated from the inner, rocky part of its home system, how did it get ejected and travel across interstellar space to us? Could it have been flung out by some colossal collision? Or was it, despite appearances, actually a comet whose volatile ices were somehow shielded by a thick, dust-like coating accumulated over millions of years of interstellar travel? These questions were intriguing. Oumuamua passed its closest point to the Sun on September 9, 2017, at a mind-boggling 87 kilometers per second. But as it sped away, something extraordinary happened. It didn't just slow down as expected under the Sun's gravity. Instead, scientists detected an inexplicable, subtle burst of acceleration, a gentle push away from the Sun. This acceleration, though minor, only about 17 meters per second when it was nearest the Sun, sent shockwaves through the academic community. Oumuamua was not behaving according to the laws of physics. Objects accelerate when they are pushed. So, what was pushing Oumuamua? Initial hypotheses were quickly dismissed. Solar winds, the stream of charged particles from the Sun, can exert a tiny push on objects, but it was far too weak to account for Oumuamua's acceleration. Scientists then turned to a more common explanation for accelerating space objects: comets. As a comet nears the Sun, its internal ices heat up and sublimate, turning directly into gas. This outpouring of gas and dust acts like a tiny thruster, subtly accelerating the comet. It also creates the comet's signature tail and coma. But here's the critical piece: scientists could detect no dust or gas emanating from Oumuamua. The Spitzer Infrared Space Telescope spent 30 hours intensely scrutinizing it, looking for any trace of infrared emission, a telltale sign of outgassing. It found nothing. This object emitted nothing in the infrared, a stark contrast to typical comets which glow brightly. Adding to the enigma, Spitzer also indicated Oumuamua was at least 10 times shinier than a typical comet, a characteristic that might align with something metallic. So, if it wasn't a comet, and solar winds weren't the answer, what was it? The inexplicable acceleration sparked one of the most fascinating scientific debates of our time, epitomized by two prominent theorists. On one side, Harvard professor Avi Loeb presented the most headline-grabbing theory: alien technology. In 2018, he argued that solar winds could explain Oumuamua's acceleration, but only if the object was incredibly thin, perhaps just 0.3 to 0.9 millimeters thick. An object 1,000 meters long and a millimeter thin is highly unlikely to form naturally. Therefore, Loeb concluded, it must be artificial. Light sail, designed to harness solar radiation for interstellar travel, a technological marvel. This radical idea met strong resistance. Darryl Seligman, then a postdoctoral researcher at Cornell, countered with a paper in 2020. He proposed that perhaps the outgassing was simply invisible, primarily composed of hydrogen. He suggested Oumuamua could be a hydrogen iceberg, sublimating quietly as it neared the Sun, providing the necessary push without visible dust. Loeb was quick to challenge this. He argued that the starlight in interstellar space would be warm enough to melt any hydrogen iceberg before it ever reached our solar system. University of California assistant professor Jennifer Bergner. Bergner pointed to laboratory experiments where water ice, under extremely cold conditions and exposed to radiation, could trap pockets of hydrogen. When warmed, the ice structure rearranges itself, releasing the trapped hydrogen gas. This was a game changer. Water ice is abundant in space, and cosmic radiation is everywhere. Together, Seligman and Bergner proposed that Oumuamua was a new class of object, a dark comet. Its acceleration could be explained by the invisible outgassing of trapped hydrogen, released as its water ice structure reconfigured. This theory accounted for the acceleration and the complete lack of dust, as no solid material was being blasted off its surface. While it didn't sway Loeb, who continued to champion his alien spacecraft hypothesis, Seligman was already looking ahead. If Oumuamua was a dark comet, could there be others? Seligman, Bergner, and their team began poring through existing data on objects within our own solar system. They weren't looking for interstellar visitors, but for anything exhibiting unexplained, non-gravitational acceleration without visible outgassing. And they found them. 6 objects, all small, some as tiny as 3 meters across, resembling ordinary asteroids with no remarkable features. These near-Earth objects were exhibiting the same subtle, inexplicable acceleration as Oumuamua, albeit on a much smaller scale. They weren't zipping through the solar system like spaceships, but their anomalous motion couldn't be explained by any known mechanism. Intriguingly, one of these objects, 1998 KY26, is already slated for a visit. The Japanese Hayabusa 2 probe, which completed its primary mission in 2020, is on an extended mission to visit this rapidly rotating, water-rich asteroid by 2031. When it arrives, we may finally get some answers to the source of its strange acceleration, potentially shedding light on Oumuamua's true nature. While Oumuamua stands alone in its peculiarity, we have had other interstellar visitors since. The second confirmed object, 2I/Borisov, was a much more conventional interstellar comet. It displayed a massive, beautiful coma and tail, nearly 14 Earths wide, a clear sign of its icy, outgassing nature. Its composition, while uncommon, wasn't entirely unusual, and its trajectory was relatively unaffected by the Sun's gravity due to its greater distance. Borisov was, in essence, a textbook interstellar comet. And then there are the objects that started interstellar but ended up trapped. Our solar system also acts as a cosmic net, occasionally capturing interstellar objects. Comets Mach-Holes 1 and Hyakutake, C/1996 B2, are thought to be such captured interstellar comets, pulled into highly elliptical orbits by the powerful gravity of Jupiter. Their highly unusual compositions, compared to typical solar system comets, hint at their extrasolar origins. These captured objects are tantalizing targets for future missions, as the solar system has already done the hard work of bringing interstellar material within our reach. Another telltale sign of extrasolar origins is a retrograde orbit, orbiting in the opposite direction to almost everything else in our solar system. Take 514107 Kakeo, pronounced Kaukaoichla. What makes this object particularly fascinating is that it's an asteroid, unlike most interstellar objects we'd expect to see. This suggests it might have been a comet whose volatile materials burned off early in the solar system's history, then captured. Its orbit is also peculiar, locked in a 1:1 orbital resonance with Jupiter. While these objects are incredibly interesting in their own right, they don't fully solve the enigma of Oumuamua's anomalous acceleration. The central mystery remains. So, if not from our solar system, where did Oumuamua come from? We know it traveled an immense distance. Astronomers painstakingly traced its path back millions of years. It appears to have originated from the direction of the star Vega in the Lyra constellation. Scientists have identified 4 possible home stars, some as far as 81 light-years away, but a definitive origin remains elusive. Today, Oumuamua is over 6 billion kilometers away, hurtling towards Pegasus at 26 kilometers per second, a distance comparable to where Voyager 1 captured the iconic pale blue dot image. Even if it's not alien technology, Oumuamua holds immense significance as the first confirmed interstellar object to visit our solar system. The questions it raised demand answers. We detected Oumuamua a mere 40 days after its closest approach to the Sun. By then, it was already 33 million kilometers from Earth. Ground and space telescopes went into overdrive, desperately trying to gather data before it vanished. But just 2 months later, by mid-December, it was too faint and fast-moving for even our largest telescopes to study. With limited data and a surplus of unanswered questions, some researchers believe the only way to truly understand Oumuamua is to send a mission after it. But catching up to it presents 3 monumental challenges. 1. Speed. Oumuamua is over 6 billion kilometers away and racing at 26 kilometers per second. No chemical rocket we have today can match that speed. 2. Deceleration. Even if we could catch up, slowing down enough to study it would be incredibly difficult. we'd just shoot right past it. 3. Location. Finding a tiny, tumbling object just a kilometer long in the vastness of interstellar space is like finding a needle in a cosmic haystack. Despite these daunting barriers, research groups are actively planning missions to catch Oumuamua. The most prominent comes from Project Lyra, launched by the Initiative for Interstellar Studies. They've outlined 2 audacious trajectories. The first involves a complex multi-stage maneuver: accelerate from Earth to Jupiter, then use Jupiter's gravity to fall towards the Sun. As the probe approaches the Sun at its fastest, its engines ignite for a powerful solar orbit maneuver, predicted to slingshot the probe out of the solar system at over 70 kilometers per second. This is fast enough to catch Oumuamua. However, it requires a heavy heat shield, limits payload, and uses never-before-attempted maneuvers. The second trajectory, while more convoluted, is arguably more feasible. It involves multiple gravity assists from Venus and Earth, a crucial deep space maneuver to reorient the probe, and a final, powerful catapult from Jupiter. This approach avoids the need for a heavy heat shield, offers a shorter overall trajectory, and results in a slower final speed, making deceleration at Oumuamua easier for better data capture. Project Lyra has identified viable launch windows between 2030 and 2033, with an estimated arrival at Oumuamua by 2048. As one of their mission designers, Marshall Eubanks, believes, a mission to Oumuamua is inevitable. After all, if we're planning missions to planets around other stars, Oumuamua will still be significantly closer even a century from now. But what if we could anticipate these interstellar visitors? Astrobiologist Karen Meach, who led the characterization of Oumuamua, believes we soon will. The Vera C. Rubin Observatory, set to become operational in late 2025, will be a game-changer. It will be able to spot objects like Oumuamua 3 months before the telescope that discovered it. Moreover, its 10-year legacy survey of space and time, LSST, will build a massive database, ideal for identifying new interstellar objects. A 2023 paper estimated the LSST could find up to 70 Oumuamua-like objects per year. Another exciting initiative is ESA's Comet Interceptor mission, launching in 2029. This probe will park in space for up to 3 years, waiting for an unknown comet or interstellar object to fly by. When one appears, it will spring into action, conducting a close-range flyby to build a 3D map. It's the first mission ever launched with an unknown target. However, these methods won't give us any data on Oumuamua itself, which is now too far away. The answers it holds will be lost to the darkest reaches of interstellar space if we simply wait for another. So, is launching an interstellar probe to chase Oumuamua a crazy idea? Technically, no. It's challenging, but nothing about it is impossible with our current knowledge and technology. But is it economically viable? Space missions demand immense resources, time, money, materials, and brilliant minds. Perhaps it's better to let Oumuamua's secrets remain, trusting that if it happened once, it will happen again, and our solar system will eventually welcome its next interstellar visitor. Ultimately, it comes down to the price we are willing to pay to satisfy our insatiable curiosity. Researchers at Project Lyra are certainly considering the investment. Is it worth it? In the end, multiple theories have been proposed to explain Oumuamua and its strange properties. But without more data, we have no idea whether Oumuamua was merely another dark comet, tantalizing proof of alien life, or something else entirely. That's the wonder of science. The more we explore the universe, the more we encounter strange and unexpected phenomena. And as we learn more about them, our theories evolve, becoming richer and more accurate. Perhaps one day, we will encounter more objects like Oumuamua, which may lend further weight to a particular explanation. The search, even for dark objects acting under invisible forces, always fills us with a marvelous curiosity. Only time will tell if these missions to gain more data will be worth the enormous gamble. But that's the terrible, captivating irony of it all: unless we take the gamble, we'll never truly know. Thanks for watching. Making videos like this requires extensive research and planning, and we're able to do it thanks to the incredible support of our members. If you'd like to see more deep dives into the cosmos, consider joining our community. You'll get ad-free viewing, your name in the credits, and access to exclusive content. Click the link in the description to learn more, and check out this playlist for more of our astronomical adventures. See you next time.